equations, but the really big ones, the kind that are supposed to be unsolvable structurally, at least using classical methods.
That's right. That's the core tension here. We've got these sources talking about a frankly approach, Ezouidi's theorem, and it tackles one of algebra's really tough problems, finding the exact symbolic roots for these high degree equations. We're actually going to look at a specific example, a huge degree 16 polynomial.
Okay, so our mission today is basically to unpack how this theorem gets these guaranteed exact solutions. Because traditional math, as you said, it mostly offers, well, educated guesses, right? Approximations. Let's paint a picture of this specific equation. Degree 16, that means what? 17 terms from 6y all the way down to a constant.
Exactly. And it's not just long, it's dense. The coefficients, the numbers multiplying the $6 terms, they're massive. They follow this really complex binomial pattern. Predictable, yes, but incredibly intricate if you were to write it all out. I mean, it's just one of the densest algebraic structures imaginable. It's the kind of thing where most mathematicians would immediately think, okay, numerical methods time.
All right, let's dig into that tension right there. Why is approximation the usual way? And why isn't it good enough in this case?
Well, fundamentally, it's a trade off, isn't it? Speed versus certainty. Your traditional numerical methods, things like Newton's method, they're great for getting close to a root and fast. But the way they work is iterative. They calculate, then they recalculate based on the last guess, refine it.
And right there, the moment you have a guess, you've got potential error creeping in.
Precisely. For an equation this big, 17 terms, all interacting, every single calculation, no matter how small, risks a tiny rounding error, a little decimal inaccuracy. By the time you've iterated maybe dozens or hundreds of times to get your final root, well, those tiny errors have built up, they've propagated. So you end up with a very, very precise approximation, sure, but you have absolutely zero guarantee that it's the structurally exact value. You don't know for sure.
And Ezouidi's theorem, promising these exact symbolic solutions, it's not just pushing back against numerical methods. It sounds like it's challenging classical algebraic theory itself. There's some history here, isn't there?
Oh, absolutely. You really have to go back to Abel's theorem. 19th century, Abel basically proved that there's a kind of ceiling in algebra. Polynomials of degree 5 or higher, generally you just can't solve them using only radicals. Simple addition, subtraction, multiplication, division, and taking roots. That finding really defined the limits for a long, long time.
So for like 200 years, the consensus was basically some algebraic problems are just fundamentally unsolvable if you stick to pure exact manipulation. You have to approximate. And Ezouidi's work just steps right over that line.
It seems to, yeah. It essentially says, okay, if single radicals don't work, let's try a different kind of manipulation. Let's use a structured recursive transformation. Instead of just aiming for a number that $6 is close to, Ezouidi's theorem offers this systematic symbolic pathway. It aims to reveal these precise, solvable roots, kind of bypassing the limitations Abel described. It's about structural certainty, not just numerical estimation.
Interesting. I read somewhere that when Ezouidi first published this, the reaction was, well, shock, almost disbelief, right? Like challenging a fundamental law. The idea that a degree 16 polynomial could be reduced like this.
That's exactly the scale of the claim. It's a major challenge, both mathematically and maybe even philosophically. If the old rules say approximate, you need a really robust new architecture to break those rules. So yeah, let's look at that mechanism. How does it work?
Okay, fascinating. So if brute force calculation leads to errors, we need something cleaner. How does the theorem pull off this symbolic transformation without introducing its own problems?
Well, the whole approach is designed to kind of peel back the layers of complexity. You start with a polynomial as given, with all its dense coefficients. The source material calls them Q. Think of these little coefficients as like the surface features, maybe a bit chaotic looking.
Right, the initial messy numbers. And instead of trying to solve using those directly, we're aiming to convert them into a new set of coefficients.
Exactly. We derive a completely new transformed polynomial. And this new one uses what the theorem calls the Q coefficients. You could think of the Ur's coefficients as representing the underlying, maybe the pure structure of the equation, like doing a really careful analysis to dissolve away the surface noise and find the core components underneath.
That's a neat analogy, the equation's DNA. But hang on, if calculating these new Ur's coefficients is itself complex and recursive, aren't we just swapping one calculation headache for another? How do we avoid errors there?
That's the crucial point. And that's where the elegance of the theorem really shows. The recursion is designed to guarantee purity precisely because of the building blocks it uses. They are fixed, exact, non-approximated values.
Okay, walk us through those building blocks. This feels like the real core of it. How do you guarantee zero error in such a complex calculation?
Right. So the recursive formula, it calculates each ES coefficient based on the original ill coefficients. But critically, it uses components that are mathematically exact by definition. For example, it uses precise binomial coefficients. Those are just combinatorial numbers like n choose k, they're known, exact whole numbers, no approximation there. It also uses the exact degree of the polynomial, that's a given, and the specific exact value of the original polynomial's very first coefficient, also a given.
Ah, okay. So instead of building with potentially slightly off numbers from previous calculation rounds, constructing the new coefficients using fundamental, mathematically pure guaranteed values.
Precisely. Think of it like traditional methods are maybe like building something complex with parts that are almost the right size. Little errors accumulate. Ezouidi's recursive method is more like building with perfectly machined components, guaranteed by their mathematical definition. Every step relies only on fixed constants and the original exact non-rounded coefficients. So the process itself ensures that every single derived is a coefficient is determined symbolically with no numerical drift.
So the complexity, the information density of the original equation, it gets absorbed and simplified, but without losing